because my wife told me I should not do it.
She didn't say it yet, did she?
Mayor reports to my wife on my activities here.
Has she?
She did.
Oh.
Okay, so from snowflakes to the moon. The reason I could come on such short notice to the meeting here is because I'm on leave this semester. Every 3 years we have a semester of leave. And the last 3 years ago, I was looking for what to do during my idle time. And I decided to think about snowflakes and their crystallization. So I'm very interested in history. So I was trying to think who was the first person who depicted snowflakes accurately, or at least sort of accurately, that looked at snowflakes really as a careful person. So you know what snowflakes look like? And my quest was to search for the first accurate snowflake. So where better to search than in Swedish folk art? I figured there must have been some person who was weaving or making a sweater or something that would have used the snowflake as a motif. So on Saturday, Mayor and I made a quest to the Historiska Museet to see if we could find the snowflake as a motif in the old times in Sweden. So this medieval reliquary, you see, has patterns that are fourfold symmetric and patterns that are 11-fold symmetric, but nothing that could be a snowflake. And then from Uppland, there was a cushion from the church from the 14th century, but this was 5-fold symmetric. And the pew from Gotland from 1300 had 6-fold symmetry. But there are very, very few things that in the museum that have 6-fold symmetry, which is surprising because it's so easy to inscribe 6 in a circle. All you need is a piece of string to do it accurately. Whereas to make 11 is a problem, or even 5 is a problem. But 6 turns out to be very rare, at least according to the things we saw in the museum. Here was a 6-fold one with Hebrew writing in the middle, which appealed to Mayer. But this was from the Baroque period, not so very long ago. So there were no snowflakes. So I'm forced to believe, well, we walked along Karlsgatan, is that the name of the street? Karlsgatan? Karlsgatan, yeah. And here we saw snowflakes in a bank. But that was interesting, since it's 4-fold symmetric. Finally, we found an accurate 6-fold symmetric snowflake, or at least a reasonable one. And the adjacent, in fact, I don't know if you noticed that the bus trip we took here went by this window. This is why my wife didn't want me to show you. So here I am investigating But actually, there were snowflakes noted earlier than this in Sweden. Olaus Magnus, who was Archbishop of Uppsala, wrote this story of the northern peoples in Rome in 1555. And why did he write it in Rome? Because he was out of business in Sweden. The Lutherans had taken over Sweden, so he went to Rome. But he wanted to write something that would explain to the people in Rome what they had lost when they lost the North. So this is a book of something like 230 short chapters about different aspects of life in the North. For example, chapter 3 is about the snow castles of children and describes in a few paragraphs the rules that are involved. For example, if you throw a snowball that has a stone in the middle, the ice is broken and you're thrown into the water. But chapter 22 is on the various shapes of snow. three different kinds. First, window frost, in the different kinds of windows they had then. And then a snowstorm. And finally, snowflakes. And apparently, this is the first depiction in Western art of snowflakes. There was progress still to be made, but at least one of them is six-fold symmetric. Now, many of you probably, or some of you at least, must know that Johannes Kepler in 1611, so 60 years later almost, wrote a book on six-angled snow, hexagonal snow. But in fact, he has no pictures of snowflakes in it, only how you would pack balls to make things that are six-fold symmetric. So the next mention of snowflakes is 25 years later by René Descartes in Les Météores. So here are some snowflakes that look more or less realistic. He evidently saw them while walking in a snowstorm in Belgium. So at the bottom are hypothetical snowflakes. He thought that there would be a little ball of ice with hairs growing out of it. And then the hairs would come together to form the branches of a snowflake. So he's interested in crystal growth. Okay. But then the final product could be stars, or fleuris, or rose. But notice in the stars something that's funny. Those are all 8-branched, not 6-branched. So he obviously was looking at them in order to draw these different kinds. I wonder if he actually saw 8-branched snow. I doubt it. And then 20 or 25 years later, Erasmus Bartholin, published an appendix in the book by his brother Thomas Bartolini on the use of snow in medicine. And so you see it also has Erasmus Bartholinus' dissertation on the shape of snow. And these pictures are the illustrations in that. So here are considerably more detailed snowflakes than Descartes had drawn 25 years earlier. And then, just 4 years later, Robert Hooke, the subject of tonight, in 1665, drew these snowflakes in his great book, Micrographia. Now, he's been accused of plagiarism. On the web you can find snatched snowflakes, which says Hooke includes an array of snowflakes that look more like caricatures than the real thing. They're copied not from nature, but from Thomas Bartholin's De Nivis Usu Medico Observationes Variae from 1661. This, incidentally, is in a web page that advertises for sale a CD of Hooke's book. With friends like that, who needs enemies? So here you can see similarities. There are six-fold branch things. Here are things with little knobs on the end. There are ones with little clubs on the end. These look sort of herringbone. And Brian J. Ford wrote, "Careful study of the images which Hooke published revealed that he himself was not above plagiarism." Hooke accused many people of plagiarism of his work. Now, Brian J. Ford, I don't know if anyone knows Brian Ford. Do you know? Then I'm free to say whatever I wish to say about Brian Ford. Here's a picture of Brian Ford from the web. He's a freelance microscopist, commentator, and a columnist for Mensa. Do you know Mensa? This is the club of people who think they are very smart. So let's ourselves engage in a careful study of these. First, there are the herringbones. So these are two herringbones by Bartholinus from Copenhagen. Here's the allegedly plagiarized snowflake by Hooke, a herringbone. And here is the experimentalist. Wilson or Snowflake Bentley, who was a farmer who lived in northeast United States, where the only thing you could do in the summer was go a few steps out of the farmhouse into the snow. So when he was very young, he got a camera and began taking pictures of snowflakes, and has generated a catalog of thousands of snowflakes, all different shapes. They're beautiful. You can buy it as a paperback. So here's a picture that Snowflake Bentley said. So this is the real thing from nature. So let's analyze these. First, let's look at the top left. You see there are primary branches and there are secondary branches. And if you look at the other snowflake of Bartholin at the top, there are primary and secondary branches. And if you look at the snowflake of Hook, there are primary and secondary branches, but they're at different angles. And if you look at nature, they're like Hook's angles, not like Bartholin's. Or we could look at the fleur-de-lis, and you see Descartes saw what he wanted to see, which was fleur-de-lis. Right, with primary and Bartholinus has this, Hook, and nature. So Descartes saw real fleur-de-lis. Bartholinus saw this shape for the secondary branches. And Hook saw this shape. And nature saw that shape. Okay, in the middle you notice there is a six-fold symmetric Mogen David, the Star of David, in the real thing. And there's the same thing in Hook. And there's the same thing in Bartholin, except it's rotated by 30 degrees. So I think the inescapable conclusion from this is that Hook was copying nature. He wasn't copying Bartholinus, and he wasn't copying Descartes. I wrote this to Brian J. Ford in an email, and he wrote back to me and said, "The flakes you chose to analyze aren't the definitive examples, I fear. The clincher is the flake labeled K." So there's Bartholinus's K, and here's the corresponding flake of Hook. Ford wrote, "Hook was careful not to reproduce images directly, but, as was the habit, to make small changes so that he could not be accused of copying. But copy he did. The K flake couldn't possibly be coincidence, and it was not, assuredly not, observed in nature." So we go to Snowflake Bentley and look at these pictures of his snowflakes, which I wrote back to Brian J. Ford, to which he responded, "This is an elegant argument. Though having looked at a great many snowflakes under the microscope, I am not persuaded." Hook was a particularly pushy and strident character, a man for whom I have unlimited admiration. But I don't doubt that he took Bartholin's picture as his source. So what this suggested to me was a question. Who was Robert Hooke, and what did he do to deserve this reputation? So I spent much of my leave thinking not about snowflakes, but about Robert Hooke. So I'll tell you a little bit about him. I won't tell you, this is a longer talk than is appropriate for after dinner. So I'll take my sweater off. But the good news is that I'm going to skip several parts of it. I'm going to skip the part about the background, about Bacon and the Royal Society and the invention of the scientific method. I'll say something, of course, about who is Robert Hooke. All these biographies of Hooke have been published in the last 4 years. He's a growth industry. Finally, he's coming out from under the influence of Newton, who suppressed Hooke for many, many centuries even. We'll talk a little bit about Micrographia, this great book from 1665. I won't talk about Hooke's codes in his top 10 list that he wanted to keep secret. I won't talk about Hooke's law and its utility, although that's why most people know the name of Hooke. I'll mention to you why he was interested in the force law. It was in order to make a clock that would be accurate, not dependent on the force of gravity being constant over the surface of the Earth, and not dependent on temperature. So that's why he was interested in Hooke's law. But I think you might be interested a little bit in his work on gravity and geometry and his interaction with Newton. And finally, just a few comments at the end about the transitory nature of fame. Okay, just to put him in context, he lived 1635 to 1703, so in the 17th century. That's when New Haven was founded, the place I live. And this is when Yale University was founded, so he lived during just that period, which my students like to know. And here we are. So if you go back 100 years, you get to Planck and quantization. If you go back another 100 years, you get to Lavoisier and oxidation. If you go back another 100 years, you get to Newton and gravitation. And another little more than 100 years, you get to Copernicus and revolution. And Columbus and navigation. And Luther and Reformation, and these things all have something in common, right? Including Bacon and the Instauration. Because they're all asking questions that people didn't ask before. And Hooke, in the introduction to his book, the Micrographia, said that the 17th century, his period, was an age of all others the most inquisitive. So this is the time when people began to really wonder about things and think accurately about them. Hooke's patron was Robert Boyle. And we know Boyle from his pneumatical instrument and his gas law. But what you might not know is that this depended on the vacuum pump in the middle here. And that was made by Hooke, who as a student was a skilled mechanic and was able to make a pump that would create a vacuum that no other machinist in England could make. Boyle tried other people before he tried Hooke. So here's an illustration from one of Hooke's works, and it could be, although we don't know, that that's a self-portrait of Hooke. If so, it's the only portrait of Hooke that exists. It's known that an oil portrait was made of Hooke, but after Newton took charge, it disappeared. He was described, though, by Richard Waller, his executive, after his death, saying, as to his person he was but despicable, being very crooked, though I have heard from himself and others that he was straight till about 16 years of age, when he first grew awry, by frequent practicing with a turn laugh. So he was doing mechanics on a lathe, and it was thought that he got a hump back from doing that. He was of an active, restless, indefatigable genius, even almost to the last. Seldom going to sleep till 2, 3, or 4 o'clock in the morning, and seldomer to bed, oftener continuing his studies all night and taking a short nap in the day. His temper was melancholy, mistrustful, and jealous, which more increased upon him with his years. He was in the beginning very communicative of his philosophical, which means scientific, discoveries and inventions, till some accidents made him to a crime, close and reserved. This was the idea of other people stealing his ideas. He laid the cause upon some persons challenging his discoveries for their own, taking occasion from his hints to perfect what he had not, which made him say he would suggest nothing till he had time to perfect it himself. And Pepys, the famous diarist, wrote of him, he, Hooke, is the most and promises the least of any man in the world that ever I saw. They were great friends. So Hooke was born in 1635, the youngest son of an Isle of Wight curate near Freshwater, where this picture is. In 1648, when he was 13, his father died, and he went to London with his small inheritance of about 40 pounds. It's a picture of London at that time. And he was apprenticed to Peter Lely. Do people know who Peter Lely was? He was Dutch. He was a painter. He was the court painter to Charles I, but he was a versatile man, and after Charles was beheaded in 1649, he painted Oliver Cromwell. And after Cromwell was deposed, he painted all the women of the Restoration Court, like Diana Kirk. Incidentally, Diana Kirk's house, her mansion in London, was built by Hooke. But it turned out that Hooke got headaches from oil paint. So he quickly quit this apprenticeship and went to the Westminster School, which was headed by Richard Busby, who was unusual in that he taught his students mathematics. So Hooke went through the 6 books of Euclid in 1 week. He became a choral scholar at Christ Church in Oxford. Now, the choral scholarship was an unusual thing during the period of Cromwell because no one was allowed to sing in church. So it was complete sinecure. But in 1655, he became laboratory assistant to Robert Boyle and built this pump. Then he followed Boyle to London and became curator of experiments at the Royal Society. So he was the Royal Society. Other people came to meet and to discuss, but everything was practical. Everything that Anne would do here was done by Robert Hooke. And he was, every weekly meeting, he was to put on 3 new experimental demonstrations for the fellows of the Royal Society. Here are some of the things that Hooke invented. The universal joint, which is in every automobile. The iris diaphragm, which is in many cameras. The double-hung window was invented by Hooke. The telephone, he said, I have, by the help of a distended wire, propagated sound to a very considerable distance in an instant, or with a seeming quick emotion as that of light. I think many of you have made such a telephone out of tin cans. Here are some of the instruments he invented. A barometer that would run a dial instead of having to look at the height of the mercury. A weather clock which would record, make a hard copy of 5 things about the weather: wind velocity, wind direction, humidity, temperature, and the barometric pressure. The reflecting quadrant, which you can see at Greenwich, including the micrometer screw and the telescopic sight. It also had a clockwork drive and a spirit level, but these were not his inventions. He just implemented them in this. And a device to measure the frequency of the wing beats of a fly. You might think about how you would build such a thing at that time. You can save that for the questions later if you want. And most importantly, the compound microscope. Before this, there were simple microscopes, just a single lens. But he invented the compound microscope, which allowed him to see things better. And he said in the preface to Micrographia, by the addition of such artificial instruments and methods, there may be in some manner a reparation made for the mischiefs and the imperfection mankind has drawn upon itself. So that in Eden, man fell and became disconnected with nature. But instruments could allow you to reconnect. Sometimes it's not working everywhere. So here are some discoveries of Hooke in science. He discovered the spots on Jupiter and the rotation of Jupiter and Mars, so astronomy. He was the first person to make figures that are named for Chladni, who came more than a century later, that are nodal patterns in the vibration of plates. So acoustics. He was the first person, or probably the first person, to think that fossils were the record of ancient animals rather than the sign of God trying to trick us. So the idea that species had disappeared from the earth and that the earth itself was mutable because obvious remains of sea creatures were high in the mountains. Right? So paleontology, geology, evolution. The role of the lungs in aerating the blood. which required grisly experiments with dogs that he refused to repeat for members of the Royal Society who had missed his original presentation. And the consumption of part of air during combustion, so oxygen. This is 125 years before the people who are usually Lavoisier, Scheele from here, and Priestley. This is a not untypical set of accomplishments during 3 weeks in October 1663. He prepared a paper on what should be observed and recorded for a history of the weather. He made and demonstrated a hygroscope from the beard of a wild oak with a dial. He prepared 2 thermometers, one of tin and the other of glass, which had been invented by Wren. See, he was the servant for the Royal Society, at least that's the way they regarded him. So they would say, do this, do this, do this. He made an artificial eye. He prepared a suitable concave glass for projecting a picture in a lighted room. So he invented the slide projector. He removed and restitched a piece of a dog's skin to see if it will regrow. He moved into new accommodations. He supervised making a new air pump and a machine for measuring the force of gunpowder. He prepared micrographs of the common fly and of moss growing on the brick. He took care of the museum of the Royal Society and labeled all the objects with where they had come from. He prepared a demonstration of a lineless depth sounder to show to King Charles, hoping to get some money. The Royal Society always hoped it would be able to get some money from the king and never did. And he grafted feathers onto a cock's comb. This was in 3 weeks. This is Gresham College, where he lived. It housed 7 professors who gave free public lectures once a week. That was the condition of their position. He lived in that area as professor of geometry. Here is a blow-up of it. And you see there's a curious structure on the roof. What that structure is, here seen in cross-section, is a big lens on a pipe with a little lid that can be opened and shut with a string in order to protect it from the weather. So when you open it, you can lie down on the ground floor on your back and look through a micrometer eyepiece through this lens at the sky. So it's what's called a zenith telescope. It's a telescope that can only look in one direction. And why do you want to look in only one direction? It's because you can look straight up and see a particular star. And you can do the same thing 6 months later and see if the star has moved. Because if the Earth moves around the sun, the star will move. So he was looking to confirm Copernicus. Right? It's supposed to say that there. Well, yeah, that's what he was doing. So 1665, he wrote his great work, Micrographia, or physiological descriptions of minute bodies made by magnifying glasses. This was the second book published by the Royal Society. The first was about trees. So here's his compound microscope and the illuminator he made from it, so the flame from an oil lamp could be focused in order to get enough light to see something at high power. And the book consists of 60 observations, the descriptions of 60 observations, which are vast in their implications. The very first, to attract the attention of the reader, is at the point of a sharp, small needle. And he showed that it's not nearly as smooth and fine as you think, but very rough. And just beneath it there at A, you can see a dot. And here is that dot viewed through a microscope. So people, this was the first really popular science book, because people could look at it and see things that were there all the time and they just had no idea of before. Observation 11, for example, was of figures observed in small sand. So he had a sample of sand and looked at it in his microscope, and he saw this thing, which is to see a foraminifer, like the ones from the Dover Cliffs. So it's the first picture of a protozoan. Or observation 12, a particularly poignant one for me, because last night for about an hour I was passing a kidney stone just after dinner. But anyhow, the gravel in urine. And he says how great an advantage it would be to such as are troubled with the stone, and I speak with feeling here, to find some menstruum that might dissolve them without hurting the bladder, and of the small diamonds or sparks within flint. And he said it's interesting that these arise only from 3 or 4 several positions or postures of globular particles. So this was like Kepler, right? He said you could have 3 this way, 4, 5, 6 in several ways, 7, more, 4 could be arranged that way. And in fact, he said, there was not any regular figure which I have hitherto met withal that I could not with bullets imitate. So we could take little lead spears and shake them and get any figure that appeared in nature, almost by shaking them together. And he said the philosophers hitherto conclude that nature in these things displays the geometrician, according to that saying of Plato, O theos geometrai, God does geometry. Right? But, he said, it's impossible to imitate exactly the curious and geometrical mechanism of nature in any snowflake. He said, I designed to get as exact and full a collection as I could of all the different kinds of geometrically figured bodies, having such a multitude of instances to compare, as in the solution and crystallization of salts, we cannot but learn plentiful information of the principles which nature has made use of in almost in all inanimate bodies. And I think we can agree from our discussions of the last few days that you can get a long way there. But most interestingly, this is the first use of the word crystallization in the English language. But at the beginning of this, I left something out. Nor have I hitherto found indeed an opportunity of prosecuting the inquiry that I designed. He wanted to do this, but the members of the Royal Society were always telling him, sew feathers onto a cock's comb or cut off a dog's skin and sew it back and see if it will grow. But he did work on the idea of self-assembly. And so here's Hooke's mechanism of growth in 1665. It starts with fluidity, a liquid, something in solution. Then orbiculation, it forms drops. Then fixation, it becomes a solid drop. And then angulization or crystallization, the drop develops facets. And then germination or ebullition, vegetation, it begins to live, like the subject of this conference. Plantamination, amination, sensation, and best of all, imagination. So look at, for example, at germination or ebullition. So observation 20 was of blue mold and the first principles of vegetation arising from putrefaction. So here's his picture of the several kinds of hairy, moldy spots. That's on leather, the mold that grew on leather. All of them nothing else but several kinds of small and variously figured mushrooms. Right? So this is the first illustration of a microfungus. He says, it does not as yet appear that I know of that mushrooms may be generated from a seed. They're assembled spontaneously. But they rather seem to depend merely upon a convenient constitution of the matter out of which they are made and a concurrence of either natural or artificial heat. They're concreted by mechanical principles. There's a mechanism. And he pointed out mushrooms elsewhere, in a candle wick. You can see the mushrooms in a candle wick. Or a Diana tree, which is a beautiful self-assembled thing that the alchemists had made from silver and mercury. He said, as far as I've been able to look into the nature of this primary kind of life and vegetation, I cannot find the least probable argument to persuade me that there is any other concurrent cause than such as purely mechanical, So this was a standard thing for the people, for him to think about at this stage was, what is the mechanism by which these things happen? Observation 17 was of petrified wood and other petrified bodies, and was the first explanation that these things were formerly living things in which the biological material had been replaced by mineral. Observation 18 was on the texture of cork and the cells and pores of some other bodies, such other frothy bodies. And this is the first use of cell to describe the unit of biological structure. For observation 54 of a louse. This is a picture that folds out to this dimension. You fold the page out twice, so it's this big. Some of you, I'm sure, have seen it. And the louse is holding on to one of Hook's hairs. Imagine living in that time when you had lice and seeing this picture of what you felt crawling out on you. Or, if you didn't have lice, you probably had fleas. This is another big fold-out. So most copies of Micrographia, these pages have been looked at so often that there are rips in them and so on. They're not usually in very good shape. To see them in the original is really striking. They're beautiful, beautiful prints. But the last observation, number 60, is of the moon, from the point of a needle to the moon. So here's Hooke's picture of a particular crater on the moon. And the previous published picture of this was from Danzig, from Hevelius. And that's his picture of the same structure. And we can compare it with a picture taken from Apollo 16 as it orbited the moon. And look at how accurate Hooke's picture is. He said he was interested in the craters on the moon and what caused them. Right? He said to conclude, therefore, it being very probable that the moon has a principle of gravitation. Bear in mind, this is before Newton. At this time in 1665, Newton was a senior student at Cambridge. Right? But Hooke said either he made shapes like this by having clay pipes ground into fine dust and dropping a shot into them would make that. Or it could have been volcanoes. But either way, you'd have to have gravitation to get such a thing. So it affords an excellent distinguishing instance in the search after the cause of gravitation or attraction, to hint that it does not depend on the diurnal or turbinated motion of the Earth, which is something that Descartes talked about. So he was interested in the cause of gravitation. Now, to backtrack two chapters, in observation 58, he talked on the inflection of the rays of light in the air, because this had to do with astronomy, with which way you would aim your microscope if the light's going to bend as it goes through the gradations of the atmosphere. So he said it's likely there's a continuous increase of rarity in the parts of the air the further they are removed from the surface of the Earth. So it will be necessary, as in the other experiment he previously described, to think about the ray of light passing obliquely through the air, which is a different density, constantly and infinitely inflected or bended from a straight or direct motion. So he wanted to calculate this. After all, he's the guy working with Boyle that knew how pressure would affect the density of air. So he wanted to calculate this and how the air's density. So in doing a calculation on this, he said we will suppose a cylinder definitely extended upwards above a circle on the Earth. Right? That's going to be the column of air we're interested in. Now, what's wrong with that? If the Earth is a sphere, what's above a piece of the Earth is not a cylinder, but a cone. But look what he says about that. He says, I say a cylinder, not a piece of a cone. Because, as I may elsewhere show, if I have time, in the explication of gravity, that triplicate proportion of the shells of a sphere, the volume of a sphere goes with the cube, right, to their respective diameters, I suppose to be removed, in this case, by a decrease of the power of gravity. That is, implicitly, the area increases as a square of the radius, but that's canceled by the force being an inverse square. So this is 1665 when Newton is still a student, that Hooke is saying there's an inverse square law of gravity. Now, 1665 was the plague. So people had to leave London, leave Cambridge, leave every place and go out to where they came from to escape the plague. And one person went to Woolsthorpe, and you know who that is? Newton. And we have the notes that Newton took when he read Micrographia before going out there. So you know what happened at Woolsthorpe during that period. There's the tree that the apple fell from on Newton's head, according to the tale. Okay. So he had just been reading Micrographia carefully when he got the idea of the law of gravity. Observation 9 is that this is the real connection between Newton and Hooke. Observation 9 in Hooke's book is the colors observed in Muscovy glass, that's mica, thin sheets of mica, and other thin bodies. So Hooke's idea of how you get colors from thin things like the film of oil on the surface of something is that light, you have different thicknesses, light comes in as a series of pulses. Descartes thought of this too. So a series of pulses come in and bounce from the top, or and move on out, or they bounce from the bottom and come out. So they come out in pairs at a certain distance from one another, depending on how thick. And that sequence turns out to be yellow. It's the sequence of the pulses that gives the color. Or if it's a little thicker, they come out further apart, and that's red. Or if it's thicker yet, they come out so far apart that they get close together again. So a weak pulse followed by a strong pulse is blue in this theory. Now, as you know, Newton had his own experimentum crucis about what light was, and he submitted it to the Royal Society for publication. Light came in through a prism and broke into a series of colors. Now, the Descartes people, or Hooke, would think that what the prism did was change the timing of the pulses. But this experiment was to take a hole and send only the red light through a second prism. Right? And nec variat lux fracta colorem, it says there. The broken light does not change its color. If it were changing the timing, you'd change the color again. Okay? So that means that light is a substance, not Hooke's waves. So Hooke denigrated this when it came to the Royal Society, saying he had already done this kind of experiment, but the explanation was different. And from that time on, Newton was his bitter enemy, from Newton's point of view. Newton wrote to Hooke in February 1676, saying what Descartes did was a good step. You have added much, several ways, and especially in taking account of the thin plates in philosophical consideration. If I have seen further, it is by standing on the shoulders of giants. Now, in that's not original to Newton. He was quoting, because that comes from Lupin's Civil War from 62 AD, and also it was in Robert Burton's Melancholy 50 years earlier. But, remember, Hooke was hunchbacked. So it's not obvious, at least certainly in these days of political correctness, how he would have taken the idea that Newton was standing on his shoulders. So he lived in Gresham College. And remember, in 1666, it was the Great Fire of London, which almost, that's not supposed to stop there, it's just behaving funny. It almost got to his house. But it's an ill wind that blows nobody good, and this made a lot of construction work, which you know of Christopher Wren, building 51 churches and St. Paul's Cathedral after the fire. But Hooke was his partner. He was also city surveyor of London and personally signed the surveying that said where you could rebuild your house. And often there were discussions between neighbors about this. So he was a great negotiator. Right? And he became rich in this process as well. There's something really funny there. There we go. He designed and supervised the entire construction of Bethlehem Hospital, which you know as Bedlam, the place for the insane hospital, which no longer exists in that form. He also built the monument to the Great Fire, which some of you must have been there, or at least been to the monument tube stop. So it's often attributed to Wren, but Hooke is the one who did it. And you can see why. This is a cross-section of the monument. So there's a spiral stair that goes up, but unlike the apartment where we live, where the spiral goes to nothing in the middle, there's a gap in the middle. So a cylinder goes all the way up the middle of the monument. And it has a basement, which is unusual in monuments. Can you guess why? Up at the top, there are little doors that open. So it's a zenith telescope, which is more rigid than his house and much longer. But it still isn't rigid enough to see parallax from the orbiting of the Earth. They had no idea how far the stars were. A 200-foot zenith telescope. So that was big science. Right? Okay, you know about his book on spring, or about the fact that he has the law of spring, but the reason was very practical. It was for navigation, to try to tell longitude. Now, he became the secretary of the Royal Society in 1679 and tried to encourage Newton to continue to contribute. So he wrote a letter to Newton, November 24th. I hope you will please to continue your former favors to the Society by communicating. You may be assured that whatever shall be so communicated shall be no otherwise further imparted or disposed of than you yourself shall prescribe. We're not going to blab it to anyone the way the former secretary blabbed my to Huygens, who tried to patent it. I am not ignorant that both heretofore and not long since also there have been some who have endeavored to misrepresent me to you. But difference of opinion, if such there be, especially in philosophical matters where interest hath little concern, methinks should not be the occasion of enmity. So we could be friends as scientists. Right? So that was the former secretary, Oldendorf. Okay. I shall take it as a great favor if you shall please to communicate by letter your objections against any hypothesis or opinion of mine, and particularly that of compounding the celestial motion of the planets of a direct motion, straight line, and an attractive motion toward the central body, gravity. Newton had not thought of it in those terms before. And he proposes at the end a joint research project. I should be glad if by perpendicular observation we could determine the difference in latitude between London and Cambridge. It had also already been done between Paris and someplace in the south of France. So we could determine this. So we can do something together for good commenting. Newton replies, I cannot but acknowledge myself every way by the kindness of your letter, tempted to concur with your desire. I'd really like to do this. Heartily sorry I am that I had for some years last been endeavoring to bend myself from philosophy to other studies. I'm not really doing science anymore, so I don't think I can do this, unless it be perhaps at idle hours, sometimes for a diversion. I did not, before receipt of your last letter so much as hear that I remember of your hypothesis of compounding the celestial motion of planets of a direct motion by the tangent to the curve and the laws and causes of springiness. So I didn't know anything about your ideas of gravity or about your spring law, right? Though these no doubt are well known in the philosophical world. And Hooke wrote a notation on this letter saying this: here pretends he knows not H's hypothesis. My own short-sightedness and tenderness of health makes me something unfit for this proposed joint project, so I don't think I'll be able to do that. But he proposes something. He says, in requital of this advertisement, I shall communicate to you a fancy of my own about discovering the Earth's diurnal motion. So how can we prove that the Earth rotates? Right? So Copernicus is being subject to experimental proof. So here's Newton's idea. You take a ball and drop it. And if the Earth rotates, the ball won't fall straight down. And if you can measure how far it moves because of the Earth's rotation, you can see that proof A proves that the Earth rotates and how much. Now, that was already known to Kepler. He referred to that idea, that it would fall to the west, as the opinion of the vulgar. But he says, aha, that's not the way it will be, Newton says to Hooke. It should fall to the east, because the top of the tower is moving even faster than the surface of the Earth. So when you drop it, it's going to go even further the other direction. And this was the opening that Hooke was looking for. So Hooke immediately wrote back to him. So he said it should describe this pattern, spiraling to the center of the Earth. And Hooke wrote back this letter, which is in the library at Yale. I've had it in my hands. It's exciting. On the first page, he says, I wish I were as sure of your correspondence and communicating as I am of your yet remaining affection to philosophy. In other words, don't give me this stuff about not being in science anymore. You and I both know you're doing it. I just wish I could count on you writing to us. And on the back then, he draws pictures. And he draws this picture and says that Newton is wrong about this mechanics. That in fact, it will describe an ellipse if it can fall through the Earth. It will be like orbiting something, right? Unless there's friction. If there's friction, then it will spiral to the center in that kind of pattern. But he said in the other picture there, let's suppose we try this experiment in London. L. N is the North Pole, South Pole. L is London. Now, London is not along the axis. It's 52 degrees north. And he says that means that if I drop it, it will fall in that great circle. So it won't hit to the east. It'll hit to the southeast. So it'll fall southeast. So he tried the experiment in 1680, and it fell just as much south as it did east. That experiment was tried again in 1791, and it was only 63%. And in 1802, 37%, 1831, 15%, 1902, 3%, and the correct answer is 0. And the reason is an interesting one. How do you know what's straight down? The way you do it is with a plumb bob. But there's centrifugal force on the plumb bob. And it turns out that exactly compensates how far it should move south because of this. So it shows you get what you expect to get. Sometimes. Okay, so Newton didn't take this lying down and wrote back immediately and said the actual trajectory will be this trefoil. That's the pattern it would actually fall if you could fall through the center of the Earth. And Newton wrote back to him immediately and said, your calculation of the curve described by a body attracted by an equal power at all distances from the center, not gravitation, but a constant force toward the center, is right. You are right about the trajectory. But what Hooke couldn't figure out is how Newton could be right. He had to have a mathematical method of calculating this that was correct. But what's interesting, how did Hooke know what was right? How did Hooke know that Newton had the right answer? It was because he did an experiment. He said, like this, that was done, such as that of a ball rolling in an inverted concave cone. Right? If you have a cone and roll the ball in that, it will follow this trefoil path. You've been in a museum where they have this thing that looks like this, and you put a coin in and it goes around. He did that kind of experiment. But my supposition is that the attraction always is in duplicate proportion to the distance from the center reciprocal. I think it's not a constant force, but an inverse square force law. Right? So attraction at a considerable distance may be computed according to the formal proposition as from the very center. You know, you can take if it's an inverse square law, you can pretend that it's only things inside that are important. Okay, so the force is an inverse square law. This will spoil the universal standard by the pendulum and the equality of pendulum clocks carried from one climate to the other. So the period of a pendulum will depend on your altitude, and you can't trust it. If the Earth's not a sphere, even on the ocean, it won't be a constant timekeeper. You need my spring. Okay? So on January 17th, he said, I doubt not that by your excellent method, the mathematics I know you possess, right, you will easily find out what the curve must be and its properties and suggest, and here's the challenge, and easily suggest a physical reason for why gravity is an inverse square law. Your excellent method, and you'll easily find out, and suggest a physical reason. This was not answered for a period of a whole year, right? 11 months and 11 months later, Newton finally replied, I am indebted to you, thanks. And Newton then, of course, wrote the Principia Mathematica, which incidentally, do you know whose signatures, or whose imprimatur it is? Samuel Pepys, who's now the president of the Royal Society. But in fact, Edmund Halley was the instigator of this publication, and had trouble because he showed the manuscript to the members of the society, including Hooke, and had to write to Newton at their behest to say, Mr. Hooke has some pretensions upon the invention of the rule of the decrease of gravity being reciprocal as the squares of the distances from the center. He says you had the notion from him, though he owns the demonstration of the curves generated thereby to be wholly your own. You can do the math, but he had the idea. Well, now, the idea in micrographia was indirect. It could be that Newton didn't get it there. He certainly heard it in the letter, but he had already done this work. He just wasn't publishing it. So, but at least Hooke thought that he gave Newton the idea. And Hooke did give him the idea of the attraction to the center. Mr. Hooke seems to expect that you should make some mention of him in the preface. Newton replies, Hooke has done nothing, and yet written in such a way as if he knew and had sufficiently hinted all but what remains to be determined by the drudgery of calculation and observations, excusing himself from the labor by reason of his other business. Whereas he should rather have excused himself by reason of his inability, for 'tis plain by his words he knew not how to go about it. Now is this not very fine? Mathematicians that find out and settle and do all the business must content themselves with being nothing but dry calculators and drudges, and another that does nothing but pretend and grasp at all things must carry away all the invention. There's always tension, between theorists and experimentalists. So Newton replies so Newton, what did Newton do about this? We'll see in a second. Newton dropped references to Hooke and downgraded others. Where he had written Clarissimus Hookeus, the most distinguished Hooke, he took out Clarissimus. So, what did Hooke do about this kind of thing? He didn't, of course, have the calculus which Newton had, but he was excellent at geometry. So in 1685, he made this geometrical construction of the orbit. So here, it's two things at once. I don't know what's with my key here. Okay, so there it is. Now you see you have impulses striking the thing that's moving, directing it toward the center. Right? And the trajectory that will follow then, first will be that arrow, but it will be deflected, then it will be deflected again, and you can draw parallelograms to show the path that it would follow of this impulse, and finally do that. And he proved that this was an ellipse. So he wrote on this, the motion of the body, therefore, is an ellipse, and shall describe equal areas in equal times. So these are the first two laws of Kepler that he did geometrically, not with calculus. So Hooke did it geometrically. That could be a bumper sticker in the U.S., I don't know. Or at least he almost did it geometrically. T-shirt, right? And he had a physical reason that the things are being bombarded by particles. Right? Because action at a distance is a pretty weird thing, you have to admit. Hooke also was interested in medicine. In fact, he was a doctor of medicine, honorary. This is from his diary, 1672, August 1st, also the 2nd, 3rd, and 4th. Drank iron and mercury. Was ill. August 31, slept ill by reason of tart at noon. Got up a little and rectified my stomach with white aniseed distillate. He kept trying different things, thinking one thing would cure the other, but mostly they just made it all worse. September 1st, drank steel, benumbed my head. September 2, at Dr. Goddard's, tasted tincture of wormwood. September 3, took 2 ounces infusion of crocosmel, which is sodium antimony sulfide. He vomited. September 22nd, took syrup of poppies. Slept well, slept and wild, frightful dreams. October 1st, took spirits of urine and laudanum with milk for the 3 preceding nights. Slept pretty well. 25th, took conserves and flowers of sulfur, after which I slept well but had a bloody dysentery the next day, so that I swooned and was violently griped. But I judge it did good for my room. December 27th, made oil of bitter almonds, put some in right ear, slept ill. He lived another 31 years. Right? He died in 1703 at the age of 67. I've already survived him as of yesterday. And he left a 10,000-pound estate and no will. That was the estate a merchant banker would have. It came from his construction and surveying work, not from the Royal Society. And it was inherited by an illiterate distant cousin who soon went through the whole thing. His unpublished works were published posthumously by Richard Waller in 1705. And here's the title page. It's dedicated to Sir Isaac Newton, Knight. The posthumous works of Dr. Robert Hooke, humbly dedicated by Richard Waller, secretary. So Newton, of course, fared pretty well. This is in Westminster Abbey. He died 1727, 24 years later. During that whole period, he was president of the Royal Society. Notice that he's leaning on, among his 4 books there, including Principia, of course, Optics, which was published in 1704, although the work had been completed 30 years earlier. But he wouldn't publish it as long as Hooke was alive, because he knew Hooke was the person who could criticize it. And he wouldn't wouldn't become president of the Royal Society until Hooke was gone either. And you know, he's been made famous by the lake, by the Bank of England. How about Hooke? Hooke may be buried in this mass grave. No one knows for sure where Hooke is. He lived in Gresham College, which is now the site of NatWest Tower 42. But he left this list of his works at the Royal Society. So this is what he accomplished. The theory of motion, theory of light, theory of gravitation, theory of magnetics, theory of gunpowder, theory of the heavens, improved practical work, improved shipping, watches, optics, engines for trade, engines for carriage, inquiry into the figures of bodies, the shapes of things, as we talked about, and to the qualities of bodies, for example, the light diffraction. Right? And 2 years ago, as of next week, he was finally commemorated in London with this paving stone in Westminster Abbey, where, remember, he went to Westminster School. Right? So I thank the people who wrote these books, who helped me out. I've talked to several of them. Also these historians of science and physics who helped me out, and our libraries, which have some great Hookeana, and John Fulton, who traded a copy of Principia Mathematica for that letter. And finally, this is Hooke's snowflake. This was used as the Royal Society's holiday card several years ago. I'm sure some of you got it. So that's the end of my story. Thank you.
Thanks, Michael, for entertaining us in such a successful manner. Other questions? Just ask it. Thanks again. It was really wonderful. And cheers. Cheers, son. Robert Hooke.
Yeah. I'll drink to him.
Genius.
Good. I like it.
It's amazing.
Oh, I should have. I should have mentioned that Lawrence contributed to buying for the Royal Society Hooke's diary, or Hooke's records of the proceedings of the Royal Society for a period of about 10 years, I think, or maybe a little longer than that, which is a volume that's about that thick, and is all available online now. It's fascinating, because the Secretary of the Royal Society was Hooke's enemy. He's the guy that leaked to Huygens the secret of the spiral spring balance wheel for a clock, and Huygens tried to patent it in England through Oldenburg. But Hooke kept his own secret record of the proceedings, which was just found in a house in Hampshire about a year ago, I think, and was auctioned quite recently, or was bought. It was going to be auctioned, but was bought by contributors to the Royal Society. Good.
Oh, sure, yes.